Okay, so here's our second one, and this is Taylor and Maclaurin polynomials, which I call designer polynomials, because we're designing a polynomial to look like other functions. And really the question is says, does it make sense that we can write functions to approximate other functions such as sine, cosine, e to the x, or any other? Yep, but it must be differentiable, and it must be differentiable have many derivatives, have n derivatives. So if we are approximating e to the x, which we all know looks like this, it depends on where we're going to approximate it. P sub n is the polynomial with the degree n, which if I said fourth degree, that means we go up to the fourth power. Third degree, if I said p sub 3, that would mean we go up to the third, or up to x to the third. Caring only about the characteristics at some c, which is our center, which we've talked about center already. What would have to be true about e to the x at that c? Well, at that point c, their values must be the same. Okay, so if I'm trying to approximate it here, the value of the function would have to be the same. I think you'd also agree that the slope would have to be the same. And to get better and better, our concavity would have to be the same. And then the next derivative probably would have to be what? The same. So really, the more derivatives and stuff we add to it, the better it gets. But what we really say are Taylor polynomials are used to approximate functions for particularly small intervals. So it might just be within a tenth or two of the function or of the center. For instance, it does seem plausible that sine of x could be approximated by a polynomial. Yeah, I did e to the x, but sine of x can also. Okay, so we kind of have a formula for it, how it's derived. I believe it's derived in the book, in the appendix. Okay, so it has to have n differentiable derivatives, then the nth degree. So if I say p sub n, we just go out to the third. Center about c is, what it is you have to find the function value at c, the derivative at the center, multiply it times x minus c, that's our center. The second derivative evaluated at c, at the center. The third derivative at c, and so on. Okay, that is a Taylor. So, but if it's centered at 0, it is better known as a Maclaurin series. So Maclaurin means it's 0. Taylor is anywhere. I always kind of joke that the fact that Taylor got his name in the book for everything, and Maclaurin said, "Hey, add me for 0." So I often say that the Jones series is when it's centered at pi. No author has decided to put me in a book yet, but the Jones series is known as pi. Anyway, all right. So what I'm going to do first is I'm going to give you the coefficients, and we're going to find the P3 Taylor polynomial. That means we need to do 3 derivatives evaluated at our center, which you have the function there, you have the slope there, you have the concavity, and you have the third derivative. Okay, that's known as the P3 Taylor polynomial, or the cubic approximation for f, centered at what? 2. All of these derivatives are at 2. Okay, so we're going to say the P3 of x, and that is very important for notation to write what approximation it is equal to, well, our first value was 7, plus our second derivative at 2 was negative 6, and then in the parentheses goes x minus 2 because it is centered there. Okay. Our third term is going to be 5 times x minus 2, but if you notice I square it, put it over 2 factorial, which you notice the power and the factorial are exactly the same. Okay, the next one is going to be, it's actually negative, so I'm going to do minus 4 times x minus 2 to the third over 3 factorial. And that is our cubic approximation for f of x centered at 2. It's also known as the P what? 3, because I have up to the third degree. Okay? So now we're going to go down here, and number 2 says, it gave you all of our derivatives. We're going to find the P4. That means we're going to go up to the fourth derivative, Maclaurin means we are centered at 0, or the fourth degree approximation for g of x centered at 0. Okay? Then use it to approximate g of 0.5. So what we're going to do is then we're just going to evaluate it at the end. So by the way, I really need to say, I should have written this, f of x is approximately equal to that. Okay? So in this case, g of x is approximately equal to the p4 of x. I got to identify what it is, which is equal to -4. Remember, there's no x on that one. Plus 2 times x minus 0, or just x, because it's centered at 0. Plus 7 times x squared over 2 factorial. My third one, which will be my third degree, is -1 times x cubed over 3 factorial. And then my last one is 2 times x to the 4th over 4 factorial. Okay, you don't need to simplify the denominators, just leave them as is. Okay, so that is my fourth degree. Now we're going to go approximate it at 0.5. So g of 0.5 is approximately equal to p4 at 0.5, which is -4 plus 2 times 0.5 plus 7 times 0.5 squared, and that's just 2 on the bottom. This is minus 0.5 cubed over 3 factorial plus 2x, it's 0.5 to the 4th over 4 factorial. Okay, and I did not compute a value for that, but I will do it very quickly. Fortunately, this takes up valuable video time, but so -4 plus 2 parentheses, whoops, wrong one, 0.5 plus, I don't think you can see it very well, 7 times, well, that's just 0.25, divided by 2, and then it's minus, I believe that's 0.125, divided by 6, and then this one is plus 2 times, I think it's 0.0625, but I'm not going to risk it, 0.5 to the 4th divided by 24. And that value is, I get is -2.140625. Well, what you think about it, yeah. Okay? So so really at the value is -4, which by the way, the only place that this is an exact approximation is at 0, which is -4. It's the only place. So the minute you move 2 units to the right, it's now -2.14. So we've moved over a little bit, and that's what happens. Okay? All right, so we're going to flip the page and go to the third page here. Okay, so I left, the third page, which by the way, these notes are posted by the time these get posted. Okay, so I gave you the formula up here, same thing as what was on the previous page. Okay? All right, so now we're going to actually find it for a function. So we're going to find the P4 for sine at pi over 4. Then we're going to evaluate it. Then we're going to find a Maclaurin for cosine. Okay, all right. So I need to have a couple columns here. I need to have the function. I need to have the center. And then I need to get my coefficient. All right. So F is sine. My center we said was at pi over 4. Now to get my coefficients, all the coefficients were given to you in the last one. So now I got to evaluate this at pi over 4, and that's root 2 over 2. So what we just found, this is f of c. Okay? All right, now I need to do f prime. Derivative of sine is cosine of x. We're going to evaluate it at pi over 4. And when I evaluate that, I get root 2 over 2. And that is f prime of c. So we need to do 3 more derivatives, so I'm going to crunch those out. That's negative sine of x. The third derivative of x is negative cosine of x. And the fourth derivative of x is we're back to sine of x. Each of these are evaluated at pi over 4. That doesn't change. Okay, this is root 2 over 2, but that becomes negative because there's a negative in front of it. Same thing here. Same thing here. All right, we're back to root 2 over 2. So this is our f, double prime of c, and so on. All right, so now we're going to go write that because we have all of our coefficients. So I'm going to say f of x is approximately equal to this was our p4 of x, which is equal to our first coefficient, which is root 2 over 2, plus our second coefficient, which is root 2 over 2 times x minus pi over 4, because that represents our center. And I'm going to put it over 1 factorial because it's easier for me to remember that the power and the factorial are the same. My next one is a negative root 2 over 2, and yes, that 2 really could go on the bottom. It's x minus pi over 4 squared over 2 factorial. My next one is negative root 2 over 2 times x minus pi over 4 to the third power over 3 factorial. And then my last one would be root 2 over 2 times x minus pi over 4 to the fourth, all over 4 factorial. Okay? All right. So that is our 4th degree Taylor polynomial centered at pi over 4. Okay, and that is known as the Taylor process. Okay, I'm going to write this out. I'm not going to compute the value for it on the video. It will actually be on the notes though. So if we're approximating the sine of pi over 4, or of 0.7, which is close to pi over 4, because that's 3.14 divided by 4 is very close to 0.7. So as long as you're doing values close, we get a reasonable approximation. So we're looking for f of 0.7, which is really approximately equal to P4 at 0.7. Yes, it is important to write all those. That is root 2 over 2 plus root 2 over 2 times 0.7 minus pi over 4 over 1 minus root 2 over 2 times 0.7 minus pi over 4 over 2. I am going to simplify the factorials at this point. I know you may say this is tedious, yes, but the whole point of doing a Taylor polynomial is to show that it can approximate for nearby values. Because we're approximating functions with a polynomial. That would be 0.7 over 24. So I said I will have that completed on the notes when I post this page. Okay? All right. So the next one, I'm going to probably run out of time for this one, so I'm going to put this on the third video. So, all right, I'm going to cut this one off looking at the time because I only have 15 minutes and that was 13. So we'll catch you on the next video. Thanks.